Hello and welcome to our pre-recorded lesson on converting from decimal to any base. So we're coming hot off the heels of converting from any base to decimal, which is actually very, very easy. The only method you ever really need to use is expanded form. But the last thing we did was the multiply add rule, which you can also use to get to decimal. But what we're doing today is kind of the opposite, but the operations we're going to do are quite different, even though that is the opposite operation, because we're going from decimal to a base. And that base could be anything from binary or octal or hexadecimal. Thankfully, the rules are basically the same for each, although there is a bit of a shortcut for binary. So let's get right to it. People usually enter numbers in decimal form. By enter numbers, I mean into a computer. So you must know how to convert numbers from decimal. So usually the easiest way is repeated division. So what this means is, even though we're usually using decimal numbers in a computer, oftentimes a computer, it would be useful for it to be in binary, or at least to be able to compare them in binary or octal or hexadecimal. So let's do that division. Repeated division is our method. And the steps are as follows. Repeatedly divide the number to be converted by the base you're converting to, and keep track of the remainder. So repeatedly divide the number to be converted by the base you're converting to. What does that mean? Repeatedly divide the number to be converted by the base you're converting to. So take the number you started with, divide it by the base you want, for example, 8 for base 8, and keep track of the remainder. Sorry, that was a little bit of a tongue twister for me. I don't know why I got hung up on it. And then second step, when you reach 0, read the remainders in the opposite order that they were found, and it will give you the converted number. So really, it's only going to get us so far to actually understand the steps by reading them out. But I wanted to read them out so that you have an idea where we're going with this. But let's just go ahead and see an example. It's actually very easy. So we want to convert 988 to octal. So this is the number 988 in decimal. We're going from decimal to octal. And this is what we're going to do. Start with the number, divide it by the base. So remember, octal is base 8. And if it's base 8, that's the base we're going to be dividing by. And then take your calculator, really any calculator will do, and figure out what 988 divided by 8 is. Should give 123.5. Now, what happens here is that it means that we have 123 groups of 8, and a half of an 8 left over. And we need to do what's called keeping track of the remainders. So this is going to be weird the first few times, but just bear with me for now. We have 0.5 as our remainder. Let me be more specific. 0.5 is our remainder. So we need to figure out what our remainder is in terms of a whole number. We know it goes into it. 8 goes into 988 128 times. Our remainder is a half. A half of what? A half of 8. So take this, multiply it, and put it over here as the remainder. This will be remainder what? 8 times 0.5. 8 times 0.5 is 4. So we're going to have remainder 4. And for now, you might not know what the heck we're doing, but just bear with me. It'll all make sense in the end. So we do this again and again and again and again and again. We take our whole number that we got, keep dividing it by the base. In this case, 123. So take 123. We're going to divide it by the base again. So divide it by 8. 123 divided by 8 gives 15. And it gives a remainder as a fraction of 8, 375. Do the same thing again. 8 times 0.375. Just on the side here, we're doing 8 times 0.375, or 0.375. What you get is 3. So our answer is actually 15 remainder 3. And again, we're going to be using those remainders, but for now, just bear with me. It'll make sense in the end. Take our answer, 15 divided by 8 again. You could probably do this part in your head. How many times does 8 go into 15? It actually goes in once, but we're going to need to keep track of the remainder, which in this case is 875. 8 times 0.75. sorry, 8 times 0.875 is 8. I'll do the same thing again. What's 1 divided by 8? Well, 0.125. Let me fix that 0. And what's an eighth of 8, or 0.125? 0, remainder, 1. 8 times 0.125 is 1. So why the heck did I get this far, or what am I doing? Well, I'll show you. It's going to be like magic. It's not really magic, though. So if we end at 0, we call it stop, or we say that we need to stop. And then we read the number bottom to top. Again, new rules, but we'll get there. Read this way. What do we see? We see that our answer is 988 in decimal is 1734 in octal. Why is it 1734? 1734. Red bottom to top. So it might seem like magic, but really it's just trying to figure out how many groups of 8 and 64 and 512 and all those numbers that we're used to going the other way, trying to figure out all those groups, but with a little less of the messing around along the way. By the way, it's a good idea to try and think of all your fractions here. So you could make a list of all the remainders. 8 times 0.125. 8 times 0.250 is 2. 8 times 0.375 is 3. And if you finish this list, filling in, your 875 and your 0.5, if you fill all that in, you'll have a nice quick reference table for doing these remainder problems. But this is how they're done, okay? Hexadecimal is done the exact same way with a little bit of a twist. And by the way, before I forget, if you need another way of thinking about this question, another little bit of practice on it, go to that YouTube link and it'll explain it to you. It's the organic chem tutor, who is actually one of my favorite YouTubers. It's awesome. So, in example 2, we're converting decimal to hexadecimal. So decimal is base 10, hexadecimal is base 16. So the exact same process is going to be followed, but the only difference is that our base we're dividing by is going to be different, okay? So our remainders will end up being different as well. So let's get started. We have a number in decimal. We're going to do repeated division. So divide by 16 because it's base 16. What do we get when you divide 333 or 313 by 16? You get 20, but not exactly. You get 20 groups. We have a remainder of 8125. In this case, take 16, multiply it by 0.8125, and it'll give us a remainder over here. It'll be 20, remainder what? Well, 16 times 0.8125 is 13. All right, 13. That's a little tricky in hexadecimal, so maybe we want to change it right now. 13 in hexadecimal, let's just make a list. Well, we know that 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. So knowing that, we know that 13 is D. So really what we have is 20 remainder D. I know it's a lot to take in right now, but we'll do it step by step, and soon it's going to make a lot more sense, okay? So let's go ahead and take our previous answer, 20, do a repeated division on that. So we take the whole, and then the remainders are what's going to give us our answer in the end. Just in case you're wondering why, this 20, same as this 20. Just like in the previous question, if you'll allow me to go up for a second, our 123, and then our 15 carried down, and our 1 carried down, and so on. Pause the video and rewind. Take a look at it again if you don't know what's going on. 20 divided by 16 is definitely 1. You can only fit 16 into 20 once. But let's figure out what the remainder is going to be. In this case, it's going to be 25. 16 times 0.25, or a quarter of 16, is 4. So it's 1, remainder 4. There's no reason to change that into its decimal equivalent because it is already in it, or sorry, your hexadecimal equivalent. 4 is a perfectly fine number. Take 1, divide it by 16. It's definitely going to give us 0 because there's no groups of 16 in 1. But if you divide 1 by 16, you get 0.0625. 16 times that is, of course, 1. So 0, remainder 1. This is kind of a case that's going to come up a lot, okay? If you're dividing by 1, of course, if it doesn't make a group, if you're getting 0 groups out of this or 0 wholes, the remainder is going to be what you started with, okay? So in the case that you're getting 1 divided by something, or 2 or 3 or 4 or 5, anything less than 16, it's going to give you back the same number at the end as a remainder, but it's nice to show all your work just to be complete, okay? I'll show you up top what happened. Same thing. We had a 1, which is less than 8, divided by 8. Of course, it's 0, remainder 1, which is that original number. So once you get better at these, you'll start to see these patterns come out. But for now, I'll treat you like you don't know anything. Okay, when did I say to stop? I said to stop at 0. We saw 0, so now we're going to read backwards. What we have as an answer, 333 base 10, is 14D in hexadecimal. I know that because I was reading bottom to top. 14D. All right, I know I kind of snaked around there, but I'm just reading our answers in the reverse order. I'm going to get what I need. You can check this answer the other way. For example, you could do expanded form. That's what I'll do, actually. You can pause the video or skip through if you don't want to see this extra little bit of help. But it's a good idea to check your work. So I'm going to check my work by doing expanded form, just to make sure that I've got what I need. So expanded form, back to decimal. I'm going to take 1 times 16 to the power of 2 plus 4 times 16 to the power of 1 plus d, which is 13 times 16 to the power of 0. And let's see what that gives us. Well, 1 times 16 squared plus 4 times 16 plus 13 is 333. I got back my original answer, which means that my conversion to hexadecimal is perfectly fine. And you could have done a similar check with exercise 1. All right, that's it for this question. So if we wanted to convert a decimal to binary, binary being base 2, we can do the exact same process. It's a little time consuming, it takes some time, but it does work. And I'm going to show this to you just so you see what's up. Now, if you understand the process we did last time, you don't need to take all this time watching this. I'm going to write it all out, but if you want to fast forward till the end, you can. But this is my whole process. I'm going to talk it out. So take 43 divided by the base, which in this case is 2, and then 43 divided by 2 is 21.5. That means you have 21, and then the remainder is really easy. I mean, 2 times 0.5, you've only got a couple options here. I mean, 2 times a half is 1, right? So your only remainders are either going to be 5 or you're not going to have a remainder at all. So really your remainders are 1 and 0, which makes sense because it is binary after all, and it's all 1s and 0s. So let's keep on going down the list. 21 divided by 2. I can already see it's going to be a remainder. 21 divided by 2 is 10.5, which is 10 with a remainder. 10 divided by 2 gives you 5. There is no remainder here, so you kind of have to add it yourself in order to keep track of it. So we'll say 5, remainder 0. Then we go 5 divided by 2. That's 2.5, which must be 2, remainder 1. Then we have 2 divided by 2, which is 1. And again, we don't have a remainder, so it's remainder 0. And we're getting really close to 0 now. 1 divided by 2 doesn't fit into it, but we do have a 0.5, which means we have 0, remainder 1. And we see our 0, which is our signal to stop. And then if we read this bottom to top, like last time, we'll get our final answer. 43 in decimal is 1, 0, 1, 0, 1, 1 binary. And that's how it's done. If you want to check it, we can use our concepts of binary. And I'll just make a little side note here as a check. I'll do it the quickest way I can think of. If we want to check that this number is indeed the correct answer, just use your ideas behind binary. This is how many 1s we have, 2s we have, 4s we have, 8s we have, 16s we have, and 32s. So our answer should be 32 plus 8 plus 2 plus 1. 32 plus 8 plus 2 plus 1 is 43. That's our decimal answer. The check is correct because it matches what I started with, and that's a good thing. So if you're not sure how to do this, go back through what I explained and do it yourself and make sure you can get what I got. But I don't actually recommend this method for binary very much. There are easier ways to do it, which is why I called this exercise 3.1. I'm going to do exercise 3.2, which is the exact same question done using what I'm calling repeated subtraction. This is what you do. You think about all the powers of 2. So 1, 2, 4, 8, 16, 32, 64, 128. We just go up until we are to this number in terms of powers of 2, but no bigger. So I don't need 64 and 128. And just follow me here. This is what we're going to do. 43 minus our highest one. Okay, it fits in. We have 11 left over. So we've subtracted a 32. I should have set up 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Should have set up this many placeholders because I've got a 32 here. So this is a 32. How many 32s I have? How many 16s? How many 8s? 4s, 2s, and 1s. So a 32 fits in. What else fits in? Well, I clearly can't fit in another 32. I can't fit another 16 in it, but I can fit in an 8, the next biggest. So I'm going to have an 8 here. What's left over is a 3. And going down the list again, I can now subtract a 2. And keep track of that. And what else can I subtract? It leaves a 1, so I can subtract a 1. Leaving 0. So I've subtracted a 1. And my final answer is this, and I've got to add in my own zeros. So again, it's kind of a process that you need to practice. But the idea is that I'm subtracting powers of 2 and figuring out how many of these, what numbers is this original number made of. So that's why it's called repeated subtraction. It's a lot easier to show how it's done than to explain it. So if you need me to repeat that, well, you're going to have to just go back and watch the video again. Okay? There's another method, which many students find even easier, which is to just figure out what that number's made of without the whole subtraction thing. So write out your powers, okay? You've got how many 1s, how many 2s, how many 4s, how many 8s, how many 16s, I'm just multiplying it by 2 every time, how many 32s, how many 64s. I can't fit a 64 and 43, like it's too big. So the number 43 is going to be made of all these numbers and a combination of them added together, okay? So take your biggest number first, work from left to right. We can see that a 32 fits into 43, for sure. What other numbers can add? And it's basically this repeated subtraction process, but more in your head. So if it's made of a 32, okay, it's made of 32 plus what? Well, 43 minus 32, I've got 11 left over, so I can't fit in a 16. How can I make 11? Well, what numbers make 11? out of these? How do you make the number of 11 out of 1s, 2s, 4s, and 8s? Well, you can have 8 plus 2 plus 1 is 11. So 32 plus 8 plus 2 plus 1, that gives us back our original answer. So again, it can be tricky, but you're trying to puzzle out what combination of powers of 2 can make that 43. And there is only one possible combination. So if you write out all your different combinations, try adding different things together. You'll get there in the end. Let me give you one more example on the side. Something simpler. What if you wanted to make the number 13? Convert it to binary. Again, just write out your numbers. 1s, 2s, 4s, 8s, 16s. Well, 16 is too big, so we can't use it. What way can you combine 8, 4, 2, and 1 to make the number 13? Well, you're definitely going to use the 8 because it's a nice big chunk of it. And then there's 5 left over. How do you make the number 5? Well, you add a 4 and a 1 together. So in binary, it's 1101. So 13 in binary is 1101. Okay, so lots of different ways to look at this. I do recommend that if I lost you along the way there, you do watch that video again and try to make sense of what I'm talking about. And worst case scenario, if it's just breaking your brain, you can't handle it, that's okay. You've always got repeated division in your back pocket, which is less problem solving and more algorithm. So choose the method that works best for you. And that's it for these two. So I've jumped down to slide 42, and I've said that it's a summary of our conversions. And it's just a bit of a flow chart. I've tried to make it as simple as possible. Basically, what we have here is it says if we have any number, it could be a 1, 2, 3, any number in any base. If you do expanded form on it, which is face value times place value, you will get the decimal answer. So expanded form is our, numbers in brackets plus numbers in brackets plus you multiply by the bases inside and so on, right? That process, expanded form. Repeated division is if we want to go from a decimal number back to some number in another base, we do repeated division by the desired base. So you divide by 8 over and over and over again, or you divide by 16 over and over and over again, and you keep track of the remainders. All right? So if you're stuck and you're looking at these questions and you're like, well, how the heck do I convert 43 in decimal to binary, which is base 2? Well, this is a decimal number, and you want to go to a different base. So you would say, well, I start with decimal. I need to go over and get a new base, a new number and a new base, so that's repeated division. So you can use this basic flowchart to figure things out. The rest here is practice, which you can find on D2L in the shell. The practice is, I believe, 1 page long. Let me just double check that. Yep, just 1 page long. And it says, perform the conversions using any method, and be very careful. This is all base 10, right? There's no subscripts, so they're all base 10. And if you're careful, you should have no trouble getting these. Try them yourself. I'm going to put up the answer now, and you can check your work. If any of them are wrong, go back and check your work again. And if you have questions on any of these, let me know. And here are the answers as promised. I noticed that this first answer on D2L, I think it might have 3 zeros in the middle, which is not correct. So be careful. It's actually just 2 zeros in the center to get the binary equivalent. But other than that, all the other answers are correct. Good luck working on these. Take your time. Make sure you don't make mistakes along the way, or else you're going to have to redo the whole question, because they're all kind of step by step, one after the other. And soon you're going to be an expert at changing from decimal to any base. The next thing we're going to do after this topic is to convert between number systems. That would be from octal to binary, binary to hex, and octal to hex, and back and forth, not dealing with decimal anymore as much. So you can look ahead to see that, and that's what to expect for the next lesson. As always, keep track of any questions you have, and you can let me know during our live classes, or you can email me with specific issues. All right, all the best to you, and we'll see you in the next lesson.